Okay.
Hello, everybody. I'm Avery. So the background is that I've sort of wanted to come to BattleMesh for the last couple of years, but I never found a good enough excuse. And I was working on Google Fiber, so I'm a Google employee. The Google lawyers require me to insert the statement on the front page there that none of my opinions about mesh networks have anything to do with their opinions about mesh networks. So this is all my personal opinions. I'm no longer working on Google Fiber. I'm still pretty closely related to the Google Wi-Fi efforts. But you know, this is sort of stuff that I learned while working on Google Fiber. Oh, is it not close enough? Is this better? Okay. Yep. All right. Okay, so I stayed up really late working on these slides, so they're not that pretty, but they sort of like will guide me along. So I wanted to just sort of talk about the difference between sort of what I call consumer grade Wi-Fi stuff, which is what we spent a lot of time working on in Google Fiber, and sort of, I guess, the kind of grassroots stuff that you guys do, and maybe there's a way to sort of bring them closer together, because I think there's disadvantages to both approaches. So if I sort of tell you the stuff we ran into while dealing with consumer stuff, maybe that can help build better mesh products. So first of all, I want to sort of just define what I call consumer grade. My definition is something that will work for people who have never installed OpenWRT. So I know there's not very many people like that, but if you just sort of imagine that kind of person for a minute, what their life is kind of like. They don't understand technology very well, and they don't want to mess with technology. They just kind of want the internet to work. And as we all know, the internet doesn't work most of the time. So it's kind of a matter of creating the illusion of a network that's not broken. And so this is my plot. I show this a lot at work about the fascinating success or lack thereof of the many Wi-Fi efforts that I've done. So this is a long-term graph. I've deleted the axis labels, but the x-axis is time, more or less for almost the entire lifetime of Google Fiber. And the y-axis is the number of calls per day per customer, sort of normalized. And so we don't talk about this giant hump. That was a very bad day. But other than that, it's more or less flat. So, you know, the beginning of time, we were kind of buggy. We got some bugs out. And it was just like, you know, more or less pretty good. We had a fixed number of calls per day, roughly. And things change every now and then. People go on vacation and so on. And this was our greatest success of all time at reducing the number of support calls. We added one knowledge base article that described, basically, if you have a particular device, how fast should you expect the Wi-Fi to go? Because everybody, you know, Google Fiber, if you haven't heard of it, Google Fiber is an internet service in the United States, only available in some cities, but it runs at a gigabit. And we did a lot of advertising about how it was at a gigabit, and of course Wi-Fi doesn't go at a gigabit, so every customer was disappointed. And what I like to say is, the only question is how disappointed would they be? And that was sort of my job. And so this article, by sort of formalizing what people didn't already know, so they didn't have to look it up on the internet, immediately reduced the level of disappointment by basically telling them, look, your little one-by-one $100 phone is not going to be able to do gigabit Wi-Fi. It's going to be able to go at about this speed, so when you try to do a speed test and you don't get 1,000 megabits, that's why. Right? And that reduced our calls by like 15%. And that was our biggest success in the history of Google Fiber Wi-Fi at reducing support calls. Right? So at this conference, it's really fun. We talk about lots of cool stuff. And I certainly did lots of cool stuff on my projects. But when you go and measure the like final end result, it's surprising what silly things will affect customer satisfaction. And customer satisfaction leads to growth of a network. Right? So if you can reduce downtime, if you can reduce complexity, if you can make things simpler to understand, you get a lot more users that way. So as a person who works at a business and tries to sell a service, we get in the habit of defining who's our competitor or what's our competition. And I know this is a place called BattleMesh, and I know from talking to various people that, you know, over the 10 years, the concept of battling has sort of gone down, and the concept of meshing has stayed pretty much the same. So I don't like to think of competition as a battle necessarily. Competition, the best definition I ever heard for it is competition is what people would do if they weren't using your product. Or what do they choose between your product and something else? And quite frequently, the competition is between your product and don't do anything, or your product and status quo, right? So I would say that if your product is a community wireless mesh, your competition is not, for example, other wireless mesh products, which might have been the concept in like BattleMesh 1.0, right? Competing mesh products. Really, your end users are not trying to choose between multiple community meshes, right? That doesn't really make sense. There's a community mesh that's available to them, and the option is to use it or not use it, right? And a few years ago, the competition with your community mesh might have been Ethernet or fiber or cable modems or DSL or something like that. That's less true now. People are not very excited about wired networks. And Google Fiber is a bit special because it's super fast. One of the things we found with Google Fiber is people don't necessarily want to use a whole gigabit. They think they do, but they've never found anything to do with an actual gigabit, right? So your competition with a wireless mesh is no longer really the fiber connection. It's really LTE, right? That's really what people are choosing. It's like, am I going to use my phone in LTE mode, or am I going to try to join the mesh and not pay for my wireless data? And LTE is taking off really, really fast. There's a new provider in India that just came out providing LTE for really low prices. So people who have extremely low income are getting like pretty large data rates in India on LTE. And it's sort of all over the world, this is sort of taking off. So if I was to say, what's the competition for a community mesh? It's LTE. And LTE is like this I find that sort of disappointing, right? Because LTE is actually is pretty good, but it's very centralized and very political and very commercial, right? So here's sort of the competition. So like from a technical point of view, how does LTE compare to your Wi-Fi mesh? First of all, coverage area. LTE, as we know, they're allowed to use high signal power. They have their dedicated spectrum. Compared to Wi-Fi mesh, you have to use low power, which means you have to have a whole bunch of nodes, right? A whole bunch of nodes generally, by default will cost more than fewer nodes. So LTE works everywhere. Mesh only works some places right now, right? Authentication, they have the SIM system. SIMs were really annoying like 20 years ago because they barely worked. They more or less figured that out now. If you're on the right provider, I use T-Mobile, you can actually get international roaming now, right? So I go to almost any country in the world, and included in my plan is the ability to download stuff over LTE without reconfiguring anything, right? With Wi-Fi, you typically get captive portals, which are, a pox on humanity. If you want to compete with LTE on the level of like the authentication system, you have to figure out how to get rid of captive portals. And I noticed like here, the meshes that I've tried here in Germany, many of them don't have captive portals. In the US, they mostly do, partly for legal reasons. But they're kind of silly legal reasons, right? Because LTE doesn't have that problem. You got mobility. If you roam from one point on the mesh to another, depending on which mesh technology you're using, if you're using mesh technology, your IP address might change. With LTE, it doesn't change. They put a lot of work into making sure the address doesn't change. They did a lot of terrible things to make sure the address doesn't change, but they made the address not change, right? Speed, LTE is not always the fastest, but it is very predictable, right? It comes from the oldest telephone technologies. It comes down to like reserving time slots for yourself. So at the very least, you might not get good speed, but you should be able to get the same speed for quite a long period of time if you're not like moving your phone around long distances. Wi-Fi has always been much more variable. If someone new pops in, it's going to slow you down. If someone leaves, it's going to speed you up. And every packet, who knows what's going to happen. And I have a few slides on why that matters. Technology. LTE, because they can use more transmit power, they can get away with fewer base stations. Because they get away with fewer base stations and they charge a lot of money, they can put very fancy hardware in their base stations. So it's always the latest generation stuff with all the latest MIMO things and like beamforming and all that stuff. With Wi-Fi, meshes, generally you have to go with whatever's cheapest and sort of saturate the world with a whole bunch of routers. And so you're using last generation stuff, but you can use more of it because an LTE base station sometimes costs tens of thousands of dollars. But a Wi-Fi base station can cost, well under $100. But it's a trade-off, and it's much easier to make a big expensive device that does what you want than to make a whole bunch of small devices that do what you want. So management, of course, is all centralized. That's politically not my favorite thing, but from a technology point of view, it makes it a lot easier for them, right? So LTE, it's much easier to run a central network than a distributed network. Wi-Fi meshes run mainly on hope. I hope it works. If it doesn't work, I hope someone will fix it. If they don't fix it, I hope I have a backup plan. Right, and this is something where, like my previous slide with the support calls, like people wanted to call Google Fiber and complain about how slow their Wi-Fi is. With a community mesh, there's not necessarily anyone that can phone and complain, right? And service, if something's broken, internet providers have people 24 hours driving around in trucks fixing stuff. Wi-Fi meshes, you have, if you're non-technical, if you're lucky, you might have like a 12-year-old child who can fix your network for you. If not, you maybe have a neighbor or something, but it's all, you don't know what exactly will happen when it's broken. And my last one is sort of phone calls. I know these are sort of passé now. I'm getting a little old because I still sometimes make phone calls. But phone calls and video chats and stuff like that are all require the same kind of stuff from the network. And on LTE, phone calls work. And when I'm here, I can't make a video call or an audio call using the network in this room because there are problems with the network in this room that make that not work. And that's true in general on the internet, is that video calls don't work very well. But on LTE, they kind of do. Well, not video, audio calls do. Does that make sense? By the way, if anyone wants to interrupt me in the middle, I don't mind being interrupted. Okay, so reliability is one of the things that sort of came up a few times in that slide. I want to tell you what I call Averys Laws of Wi-Fi reliability. There are 2 laws. One of them is when you replace your router, it almost always makes it better. It doesn't matter if you replace it with a better router or a worse router or an equivalent router, as long as it's different, right? So the statistics work like this. Imagine, your router that you have right now doesn't work in about 10% of situations, and you have one of those situations. Right? So imagine that you get a completely different router or a different firmware, and it also doesn't work in about 10% of situations, but it's a different 10% of situations. The chance that when you switch routers, the new one will fail in the same situation that caused you to switch in the first place is very small. It's only 10%, right? So on average, your probability of both routers not working is only 1%. So when you switch, you almost always get this benefit as long as you only switch when your router is broken. Right? And that's what people do, right? They buy a router, and if it doesn't work, they throw it away and get a new router. And people just keep doing that until they eventually get one that works for them. But it's a statistical anomaly. Like people at work, we made a new Wi-Fi router version 2 that replaced the version 1. And of course, statistically, we had this really nice graph that someone drew of how much happier the customers are when we switch them over to version 2. But version 2 was not technically any better. It was just version 2. It was a cost-reduced router. There was nothing special about it, right? So I had to go through a lot of work to explain to them, like, the reason the statistic looks like this is we never give anybody a version 2, and then they complain, and we downgrade them to version 1, right? That never happens, because we don't make version 1 anymore. We make version 2. So we don't have any statistics on how much happier they would be if you switch people from version 2 to version 1. But it would be the same statistic, right? And so you get this weird trend that the newer version always seems to have happier customers, and all of your reviews are like, hey, when I switch to this new version, I'm so much happier now, because when things are working, people don't upgrade, right? So it's this specially self-selecting group that is susceptible to this sort of mathematical weirdness. The flip side, though, and this matters a lot for mesh, is if you're adding additional Wi-Fi routers. A Wi-Fi network is basically flaky unless all the routers that are accessible to you right now are working perfectly, right? So the problem is, if one of your routers works about 90% of the time, and you add a second router and it works about 90% of the time, the probability that both of those routers are working at any given time is only 81%, right? And the more routers you add, the lower the probability that all the nodes in the network are working well. The problem with that is in a giant mesh network, you always have lots of nodes, and they might not be working. With LTE, they have fewer stations. They're going to get very loud complaints if one of those stations goes down, so they make sure that station works, and they have less of this problem. So this is one of the most important things. We found in Google Fiber, when you add Wi-Fi routers, people phone more often, not less often, because it doesn't improve reliability, it actually decreases reliability. Except for one thing. This is what I call the buddy system. It works in many different situations. It works if you're in a bar and your buddy sort of pokes you and say, hey, you're being a jerk, shut up. But it also works in the case of Wi-Fi. If you have a lot of nodes and they're all within view of each other, the trick is to have one of the nodes or every node sort of call up a buddy every now and then, connect to it, and make sure that node is actually delivering packets correctly. If you don't get a buddy calling you every now and then and telling you that everything is good, you should shut yourself down, because things are a problem, right? So if you do that, you sort of flip the statistics around. Now you've only got nodes that are actually working, if you've implemented this correctly. So now you've got, okay, router A is 90% working, router B is 90% working. The probability that both are broken is only 1%, right? So instead of the probability of both working, you can now use the probability that both are broken, which is a much better thing to be optimizing for. So it's really tricky, but I know that most people building meshes don't think about this. They've spent so much time trying to make the nodes work and trying to make the nodes perfect that they sort of miss out on this benefit of having a lot of nodes, right? So you have to make it kill itself when it's not working perfectly, and then somehow send a note to someone saying like, hey, I need someone to come fix me, or reboot, one or the other. Another thing that's pretty important nowadays, LANs are kind of passé. Nobody really wants to be on a LAN anymore. People want to use the cloud. And they want to have their own like virtual array of personal devices that are all over the place and plugged into LTE or Wi-Fi, or maybe they went to work and they want to access their files and stuff like that. So LANs are kind of, the more we think about LANs, the more we sort of get misguided. What we really want is a giant world of internet stuff that's connected. And if we have that, then the idea of configuring a router by like plugging it into your LAN and then going to 192.168.1.1 or whatever and typing in some stuff doesn't really work because there's no LAN. And so with LTE, for example, there's no LAN. And so if I want to install a mobile app that will let me configure mesh nodes, then that mobile app is probably going to be on LTE because most people are kind of lazy and are not going to try to join the mesh just to configure their mesh, and it might not even work if you tried to do that. So you need kind of some other node on the internet that will collect your configuration information, and then you need to get that configuration information back down to your device. But your device is brand new, and it doesn't have an LTE modem, it only has Wi-Fi, and there's a mesh nearby. How does it find its way to the internet? So assuming you don't have a completely wide open mesh that everyone can join, which I know a lot of people here do, but not everybody has this. We worked on a system that basically, there's a secret SSID for an auto configuration network. Devices can join this auto configuration network and are only allowed to talk to a certain subset of servers. How you figure out that subset is a little bit political. But assuming you have a subset of servers, any device that you plug in can then get through to those servers and do only enough configuration at a very low bit rate to just download their settings. The settings will include authentication information for a real network, right? So by doing that, you can sort of create this illusion of my own personal web of devices without requiring the LAN option. So this is something I've been trying to push. Nobody believes me, but I'm hoping that we can come up with some kind of standard for what's a way to create an auto configuration network that every Wi-Fi router can have, that every device will be able to join onto this configuration network and use that to grab its configuration from wherever it is at the time. I think the world of Wi-Fi would work a lot better in that case. And of course, LTE already has this. Oh. Sure.
So you will be able to auto-configure your new node if you're close to another node that shares its configuration with you.
Cool. All right, so we'll hear about that at 6. Uh, and I'm very excited about that if you're doing it. And maybe there's a way to generalize this so that you can have information floating around in the network and you can allow people to contact certain servers to get their information or something. So it doesn't have to be, depending how you want to build it, right? But I love the idea of having configuration floating around. So anyway, this is something that I think if you want to compete with LTE, you put a SIM card in and everything just works everywhere, right? There's no real reason that you physically need a SIM card except for all the politics that were around in cell networks at the time, right? It's just really a magic number. If every device has a magic number, which nowadays most of them do, there should be a way for them to get their configuration. There just isn't right now in Wi-Fi. So I wanted to talk more about the video streaming, and this is one of the things sort of dear to my heart, because in Google Fiber, we did a lot of streaming video, and of course, Google has YouTube, and of course, there's Netflix, and people are very, nowadays, most of the bits on the internet are spent streaming video around. And so I wrote a tool called ISOStream, so this is my plug for ISOStream. What it does is, it's a little bit like iPerf. You guys all know what iPerf does, right? Except that instead of going at the fastest speed it can go, it goes at the speed that you tell it. So in this case, if it prints out this ongoing update of how it's doing at 5 megabits. And so offset means, are you ahead or behind where you think you should be if you're going at 5 megabits. And so right now the mesh is working pretty well. And so I'm able to keep up at 5 megabits, but maybe if I increase it to 8, say. Oh, 8 is working too. I want to find the perfect number so that you can see sort of the glitches that happen. Yeah, so that's not the perfect number because it's slowly falling behind. You can see that the offset is slowly increasing. If I go somewhere between 8 and 12, you'll see that it sometimes falls behind and sometimes catches up. And so that's okay if you have a non-live video stream. If you're not trying to have a real-time conversation, all you really need to know is how far behind does it fall, and for how long, and how frequently does this happen, right? And with those numbers, you can do a little statistical analysis and say, okay, I need this much pre-buffering, and as long as I pre-buffer this much, my video will be great, right? Within 99 percentiles or something like that. So we did a lot of this sort of experiment on Google Fiber, but this is one of the things that right now we don't really know about our meshes because we don't measure that kind of thing in this way. I also have a couple of other tools. This one, this one I call Blip. So if you happen to have a computer in front of you, you can go to gfblip.appspot.com, and it's my completely web-based ping plus graphing program. And it works on pretty much every platform. So you can run it on your phone, you can run it on a tablet or a laptop or whatever, and you sort of get the same user interface. But I want to talk about jitter, because for live streams, jitter is just as important as this variability in bandwidth. So jitter is the variability in latency. And so what Blip does is it plots on the y-axis the number of milliseconds for a ping, and the x-axis is time. And green is like a nearby server, and blue is a farther away server. So you can see in this case, the green's nearby server seems to have this periodic kind of like, takes longer to respond, and then it goes fast for a while, and then it takes longer, and then goes fast for a while. I don't really know exactly what's going on there, but that's the pattern. Blue is super consistent. You know, seems to have a nice, pretty stable latency. But every now and then, it sort of jumps up like this, right? So the quiz question is, if I'm talking to blue and I'm doing a real-time video call, how much latency do I have to have in my video in order for the video or audio stream to not break up every quality video? Can anyone tell me what the latency would be reading off this chart? So that answer was the frame rate of the video. So the actual true answer is this dot here. The worst latency you get within a certain percentile is what affects how much delay you have to add to the video. The reason is, if I'm sending you frame, and they're all, say, 25 milliseconds delayed, then I can display you video with 25 milliseconds of latency. But then one frame arrives late, right? So this one took 400 milliseconds, right? If that frame arrives late, then I either have to pause the video or I have to forget that frame, right? Both of them cause a glitch that humans don't like, right? In audio, one of them sounds like, usually you insert crackling to make it sound more understandable to humans rather than just silence, but humans don't like random delays and they don't like randomly missing packets. So in order to make it perfect, you have to do this pre-buffering based on the worst case scenario. And so that's why this jitter is absolutely deadly to any kind of real-time streaming. And Wi-Fi has lots and lots and lots and lots of jitter. And Wi-Fi meshes just multiply that jitter with every single hop. Whereas LTE, this silly time slot thing, which is so inefficient and complicated and old, makes that problem go away. So they have kind of crappy bandwidth, and they have kind of crappy latency, but it's consistent latency. And if the latency is consistent, you can actually have lower latency video than the average latency of Wi-Fi, if that makes sense. So you can visit Blip. Actually, maybe I should pop it up right now. Let's see. I'm very proud of this little tool. I wrote it in like a day at one point. It also tests DNS. So this is the real. I took that screenshot in my hotel room last night. This is what it looks like on whatever I'm connected to in here, which is some kind of mesh network. And you can see the green dots, which are supposed to be nearby, are extremely flaky. And the blue dot is it's definitely not as nice as that graph that I was showing you, right? So if I was trying to do video, which I was yesterday, with all of these blue dots, things get bad. And they get bad pretty rapidly. There's another feature which is sometimes relevant. If you click the DNS box, it'll force every single ping to do another DNS lookup. And so it turned out, and at least on Google Fiber, that people complained a lot about slow internet. What they were actually complaining about was a slow DNS server. And this network, the DNS server, is working great. On one of the other SSIDs in here that I've played with, the DNS server is extremely bad. So it looks like the internet is working okay, but you turn on this DNS checkbox and the DNS is just like completely out to lunch. And that's why the internet seems slow on that link. So you can run this on any network basically. This one connected automatically to somewhere in Hamburg. How does it work? How does the DNS thing work? Oh, so okay, the original problem was pretty embarrassing. It was one of our testers using our router, and the way this router was designed, this was before I did any of the work, so we contracted it out. It used some proprietary Wi-Fi router firmware. They had a DNS resolver in there that tried to race two requests. So if you have two upstream DNS servers, it would actually query both of them, and then return the answer from the first one that answered. Right? So that's pretty good. That's, if one of the packets gets lost, it doesn't matter because the other one answers. Unfortunately, they had a bug where if they didn't get the second answer, they never cleared that entry out of the hash table. So eventually the hash table would fill up, and then they couldn't do anything. So if you had more than like 100 DNS queries in the last 5 minutes or something like that, the whole hash table would be full, and then every DNS query would take like 2 seconds because that's how long it took for something to fall out of the hash table. So that was really dumb, but we found it by using this tool. In general, this racing technique works really well because DNS is incredibly susceptible to lost packets. And the internet has a lot of lost packets nowadays. So you just have this natural high percentage of DNS requests that will take 2 or 3 times as long, or 2 or 4 times as long as they should, which is pretty gross. If you race connections, then it basically, if that happens 1% of the time, now it'll happen 0.01% of the time, which is a lot less. But yeah, this makes a huge difference fixing your DNS. And then I have ISOPing, which is another tool I want to advertise. Okay, I'll just type it. Oops. So ISOPing requires a special server, which is kind of annoying. But it gives you this benefit of calculating both the upstream and the downstream latency separately. And it does this it can only do it within the precision of the minimum RTT, but it tracks what the minimum RTT is from all the pings that it's done so far, and then it divides up the latency of any individual ping based on that. So there we go. So we just had some sort of problem with the Wi-Fi here. It looks like there was a huge delay in receiving packets and a little bit of delay in transmitting packets. So there was some kind of interference there. But this is extremely valuable for debugging Wi-Fi problems because almost always your Wi-Fi problems are in one direction or the other. It's very rare for your Wi-Fi problems to be bidirectional. So trying to figure out which one it is can be kind of annoying. You end up having to resort to packet traces and stuff. This just lets you ping directly. I had to make, there's an appinwire.ca that's was originally in Canada, but now in California, so the .ca is still relevant. I made an eu.appinwire.ca so that it would minimize the sort of transcontinental part of the test. Ideally, ISOPing is running on every Wi-Fi router, even locally, so you can ISOPing to a Wi-Fi router and leave out the internet part of your equation. But I haven't, and it's a very small tool. It would be great if people would package that into their routers. It's running on every Google Fiber Wi-Fi router already. Okay, so after all that talk about jitter, I want to give a plug to the huge amount of work that has gone on in the Linux world in the last little while to actually try to reduce the jitter. And it's been very successful, although only on, I think, one driver so far. Although I might be wrong. Maybe it's also works on the MediaTek driver. Is Felix here? Does he know? Eh. It works on App9. It does? Oh, okay. Okay, so it's only in App9K so far. But these are sort of compressed GF Blip plots. And what you can sort of see here, I just did the same thing 3 times. So this is an idle network. And this is what happens when somebody else is downloading at the same time. And this is what happens when somebody else is uploading at the same time. Right? So those are 2 different cases, because when you have the same access point downloading, the access point can decide who it's going to send packets to and sort of cycle them. With uploading, it's whoever got the air first. So the uploading is pretty hard to control because Wi-Fi nodes just grab the airtime and do whatever they feel like. So you can see that obviously uploading has much worse latency effect when somebody else starts downloading. But even downloading, you can see like the blue line, and this is a logarithmic y-axis. So this bump in the blue line is similar to the bump in the green line. But you can see it destroys the latency when somebody else is around downloading. When you add the airtime fairness feature in, you can see that green does get a little worse, but that's on the order of about 10 milliseconds of added latency, which is not a big deal. And blue, you can't even see the difference when more people are downloading. And then for uploading, which we have no real control over, it's still better contained. And it turns out that the fact that we have airtime fairness in the downstream direction sort of convinces the upstream direction to slow down, usually, because they don't get their acts fast enough. So even airtime fairness downstream helps fix the upstream latency. And it's hard to necessarily get the idea of it from this graph, but this is orders of magnitude improvement in jitter. And especially if you've got multiple hops of a mesh, it just makes an incredible, incredible difference. This is the difference between being able to have an audio or video call on a low bandwidth connection or not. And it's just a pure software fix. So everybody who can upgrade to the latest OpenWRT should definitely turn on this feature because it's absolutely amazingly effective. It's only on App9K right now. But it is possible to port it to other drivers, which I'm hoping people will. Certainly App10K is going to get it or has gotten it. Did someone raise their hand? No. Okay. Of course, there are many other things to worry about. So we spent a lot of time when we're building Wi-Fi extenders in Google Fiber, figuring out what's the best place to put your Wi-Fi extender. So this graph, it's a little confusing. So the x-axis is distance from the central access point, and the y-axis is the throughput that you get. And the 4 lines are the number of antennas, like MIMO streams, on the client device. So imagine that you have a 4x4 main access point and a 4x4 extender. The client is always at a fixed location out here somewhere, I think at location 100 or something like that. Right? And what we're doing on this graph is moving the Wi-Fi repeater from right next to the access point all the way over to right next to the station. And so it makes sort of logical sense if you have a 1x1 station and a 4x4 repeater. It's actually generally better to have the Wi-Fi repeater right next to the station so that you get the really high bitrate encoding because they're right next to each other at 1 by 1, and then you get the low bitrate encoding but at 4 by 4 for the backhaul back to the access point, right? But as your client gets better, the optimal location of the repeater sort of changes. The typical clients right now are 2 by 2, so that's this blue line, and you can see the right distance for your repeater is a little bit, I would say it's about 2/3 of the distance from access point to client. So the repeater should be closer to the client, but not super close to the client. And of course, nobody is ever going to do this by hand, but this sort of thing actually matters. And what you end up having to do in real life is give them a lot of repeaters and then have a good mesh algorithm, which is what a lot of you guys spend a lot of time talking about. A good routing algorithm that will choose which repeater to use in which situation and try to bounce the client to the right repeater so that you can get the optimal performance. And I know that there's not a lot of work on Wi-Fi client steering right now. Getting a client device to attach to the right access point. There's a lot of effort spent on routing between mesh points, but we sort of assume that a client that connects up to whatever mesh point is as good as it's going to get. We spent quite a bit of time on Google Fiber working on client steering, and we got some patches into host APD that help with that.
I'm sure, I mean, at least from my point of view, we work with just the routers because we can get into the user's computers.
Right.
And how do you manage that? I mean,
That's a good question. So the question was, how do you even get a client to connect to the access point that you want it to, because we don't have control over the client device. So with LTE, they once again have the advantage because LTE decides what base station you're talking to. If you talk to the wrong one, it sends you to another one, and your client must do exactly what it's told or it doesn't pass certification. With Wi-Fi, it's the other way around. The client device is supposed to pick what access point it wants to talk to. But the tricks you can play are basically, you let the client join, but then you kick it off the network, and then when it probes for the same SSID again, you tell everybody but the right one that they should reject his connection, and then he'll eventually connect on to that one, and there's things like that.
we were thinking about that because in some places when we help people having complete networks, these places that have a lot of tourists, what happens is when you see an open Wi-Fi router, you just connect. And if you're in a beach with 200 people and all try to connect, then these routers don't
Yep.
work. So we are thinking about putting a cap on the amount of users that we're going to have associated. And when you get to that cap, just tell the router to stop announcing the AP.
Right.
But it could be also done that you just tell other routers to announce the network instead of you.
Yep, exactly.
And distribute the users evenly.
Right. Yeah, and enterprise grade, like $1,000 access points have this sort of feature included. And so Google Fiber, we worked with a contractor who contributed some patches to host APD that actually lets you arrange for this kind of logic. So you can tell host APD, like, reject this MAC address or accept this MAC address, and they can sort of coordinate with each other to help bounce it from one place to another. I can't remember if those patches have been accepted or not. They were almost accepted last time I looked.
How well does the kick-out work? Because I remember that some clients actually kicked out.
Yeah, it's very fiddly. So the question was, how well does the kicking out feature work? So there are client types where it does work and client types where it doesn't work. If you implement it the right way, then you can avoid the blacklisting thing. But you have to be really careful about it. This requires kind of like careful testing.
Is there any documentation about how to implement it in the right way?
Well, supposedly the patches that we provided implemented in the right way. The main thing is you try to kick them a couple times, and if they just are absolutely persistent about it, you let them back in. Some devices you just have to do that, and there's nothing you can do. But generally speaking, Wi-Fi devices are pretty resilient about access points randomly dropping and coming back, and so they're pretty good if you kick them out once and they absolutely insist on coming back in, then most people won't notice a difference. They'll notice a couple seconds of outage, but then it'll stay up. But since you're not doing it very often, it doesn't bother them. But most devices now are pretty good. There's also the 802.11v standard. has some features in it to actually just tell a client to move from one station to another. So unfortunately, almost nothing supports the 802.11v standard, but we worked with the same contractor to make sure that WPA supplicant does support the 802.11v standard, which, okay, WPA supplicant is used by Android and Chrome OS. They just use old versions, so eventually they will probably catch up and end up supporting this feature. Yeah, so the idea is on host APD, what you do is you try 802.11v first, and if they ignore you, you give up and use the shoving them away feature. Okay, so all of that was like, why life is hard. Here's a bunch of things you need to work on. I also have a section that I'm calling good news. As is, if you've ever seen my presentations or read any of my blog posts, the good news section is always shorter than the bad news section. But people tell me, like, Avery, try not to depress everybody. They say this at work. It's like, okay, you can do a presentation, but try not to be depressing. I'm like, okay, I'll try not to be depressing. I will end on happy notes. First of all, Wi-Fi is getting faster very quickly. Of course, so is LTE, but I'll get to that in a second. And some of this is sort of marketing exaggeration, but some of it is actually not. All of the speeds in this graph, anyway, are actually achievable by real-world devices. And so you'll see like routers that are labeled 5,900 megabits or something. Obviously, that is completely made-up garbage. But you actually can now, today, buy Wi-Fi chipsets that actually can do more than 1,000 megabits on 80 megahertz channels. You don't even need 160 megahertz channels. So this exists. Of course, it only works like 3 feet away. But it's better than having a wire. And if you're 6 feet away, it's still like several hundred megabits, which is pretty good. And this rate is increasing, as you can see, exponentially. And that's not likely to stop, because that's how Moore's Law actually works. And Moore's Law, although it's slowed down for CPUs, is still very much in effect for DSP type applications where everything is parallelizable. So, good question. Is that a world of illusion where you have all the spectrum for yourself? That is, I have a couple of slides to answer that exact question. But before I get to that, I just want to say here are some statistics that I got from Google Fiber. A couple of years ago, a year and a half ago, I made a presentation somewhere else where I presented this graph. The text is super teeny tiny, but I will read it for you. It says 1 by 1 802.11n. So the most common devices on the internet are on the Wi-Fi are 1 by 1 802.11n. Second most common is 2 by 2 802.11n, and then these ones are 1 by 1 AC and 2 by 2 AC. The colors correspond to 2.4 and 5 gigahertz. So 5 gigahertz is the red and 2.4 is the blue. In January 2017, I collected the same data and drew the same graph. So you consider this sort of normalized. This is maximum. So still the most common is 1 by 1 802.11n. But you can see that AC, as a relative height to this bar, is definitely growing. And definitely, they're all growing relatively to this one. So what we're seeing is almost all new devices are coming out with 2 by 2. Which is great for reasons I'll get to in a second. And almost all new devices are coming out with 802.11ac because it doesn't cost any more than 802.11n. You build the same chip and it's like the new technology and it's the same price. And then there's a teeny tiny number of 4 by 4 devices now visible in the world. And these are 3 by 3 devices here. So the real devices, most of them are still terrible, but there is very definite progress toward them not being terrible. I have this graph. I think maybe I'll skip over it a little, but this is a picture of, the most important thing to look at here is this flat part of the graph. And I drew this a couple years ago. So it shows 2 by 2 802.11n client device. When you're, the x-axis is distance in a unit I call on and steps after my intern, who I made him do all these tests. And it's however far on and walks in one step is an on and step. And I like using on and steps because it prevents people from trying to draw like completely literal conclusions. Like if you're exactly 60 feet away, your performance should be exactly this. It's like, sometimes on and is drunk. Sometimes 60 steps is further than other 60 steps, right? So try not to be too specific about it. But the idea is when you're this close, the speed actually peaks. It maximizes because you've got so much signal to noise ratio that you're not taking advantage of it. And so one of the big differences with the new encoding rates in 802.11ac, and this leads to marketing, is that they extended it so even at this distance you get the same performance, but as you get closer and closer, you would get faster and faster performance. So they've kind of maxed out this curve now. So if you're like 3 feet away, you get the most speed you can possibly get for 3 feet away, where before you never used to. And then with repeaters, that's sort of, this is if you add more repeaters. Oh, one of the other things I wanted to point out is everyone always says when every repeater cuts your throughput in half. That's not really true. That would be 1 over 2 to the n. It's actually 1 over n. So if you have 2 repeaters, you have divide by 3 instead of divide by 2. So from there, I wanted to identify a really important thing that we discovered while building Google Fiber, which is that people do not use all the bandwidth that's given to them once you give them enough bandwidth, right? This is a super important outcome because it really changes the way you think about a lot of stuff. And you don't realize it until you start working on it, or at least I didn't realize it. But like when you give people a gigabit, it doesn't actually cost you any more than giving them 100 megabits because they're not using any more backbone bandwidth, and it's fiber anyway, and the fiber can do a gigabit, and it just doesn't matter, right? The same thing is true in Wi-Fi. So once your Wi-Fi is fast enough, the congestion is going to start falling. You've got a question.
What if they do use the gigabit? Do you throttle that?
On Google Fiber?
Yeah.
So we do have, I think, something like 0.01% of users do use their gigabit all the time. And I have a friend who knows somebody in one of the cities who does this. And he actually told me that this guy is doing it, and he's sending data to his friend 24 hours a day at a gigabit, back and forth, because it's bidirectional, so actually 2 gigabits, because he's sure that we definitely must have caps, and he's going to find the cap, and then write an angry blog post about it when he finds out what it is. But there is no cap. I guess there would have to be, if everybody was doing that, I guess we would have to have a cap, because sooner or later, like, it's expensive. He's actually doing it wrong, because he's sending it to his next door neighbor, which doesn't even cost us anything, because it's... Anyway, but yeah, it turns out so few people even come close to a gigabit that you can actually load lots and lots and lots of people onto a single gigabit link, which we didn't even do, but if we had, you would still not notice. Which, what happens is beyond a certain speed, it just means you download faster. It doesn't mean you download more. And so you just end up using less of the link to do the same thing as you used to. And that means you collide with other people that much less. And so over-provisioning of the speed or under-provisioning of the speed matters less than it used to. And this is going to start happening in Wi-Fi because we're all used to thinking about Wi-Fi meshes in terms of like, oh, well, I wonder if I can get 5 megabits or 10 megabits, and how many hundreds of users can I fit on my 5 or 10 megabits? But that's not really what's going to happen, right? What's happening is hundreds and hundreds of megabits or thousands of megabits as Moore's law continues at pretty reasonable prices. And the number of nodes we can add is going to increase because the routers are going to be cheaper, and I hope that we will be able to improve the stability and configurability, so you just like slap dozens of them in a neighborhood. And then you don't have to care that much about channel overlap or am I wasting spectrum or any of this stuff, because most of the time the network should be idle. And so you won't be fighting as much as you used to. And I personally, when I started on Google Fiber, I couldn't believe this was true. I'm like, people are going to find something to do with this bandwidth. But a gigabit is a lot of bandwidth. And people don't even need even close to a gigabit right now. But if you think about, our customers, you ask them like, well, what would you do if you had a gigabit? They're like, I would run 2 Netflix streams at the same time. And it's like, well, you didn't need a gigabit for that. You could actually run 200 Netflix streams at the same time. It's impossible for them to comprehend, right? Like you can get 3D, 60 hertz, 4K VR, and it would still cost only a tiny fraction of your gigabit, right? So we're getting to the point where it's just nobody can think of what they're going to do with all this extra bandwidth. So you have to understand that the requirements for bandwidth are increasing slower than the availability of the bandwidth. So I'll summarize that quickly through the microphone just to say, so the thing is, wired links are very different from wireless links because everyone has to share the same wireless backhaul, and the wireless backhaul is a lot slower than multiple gigabits that Google Fiber has. And that's definitely true. So I guess what I'm trying to express here is that it hasn't happened yet. We're not there right now, right? In the wired networks, it's already happened. Wired networks are so much faster than what we need that they're over-provisioned. And that's why LTE, like if we're Google Fiber, when I started off by saying our competition is LTE, Google Fiber's competition is also LTE, and LTE and Google Fiber are like very much competitors, even though the speeds are completely unrelated to each other, right? Like LTE gets you a few megabits, and Fiber gets you 1,000, right? But it doesn't really matter because people care more about these other things than they care about that extra speed that they're getting. So wireless, the kind of picture I'm drawing here, Wi-Fi is getting faster so fast that we're almost at the point where it's not going to matter with your wireless backhaul either. And I realize this is hard to believe because it doesn't feel like it, and it didn't feel like it to me even with wired networks until I started working on Google Fiber and it happened, right? I couldn't believe that it was true, but it happened. And so there's this really great book, the reason this title is The Innovator's Dilemma. I highly recommend this book because it talks about numerous times in technology that this has happened and people didn't see it coming, and then 1 year, the lines crossed. The capability of the lower powered product crossed over the demand line, and the next year, the original high value competitor died.
So I would love to continue this conversation with you because I think there is a lot to talk about. I'm not trying to be the advocate, but the thing is that when you use cable, you have an abundant resource.
Mm-hmm.
When you use spectrum, you have scarce resource that everyone is competing to access.
Right.
And the way that wireless links are increasing in speed is by taking more bandwidth. And bandwidth is...
So I actually have a slide about that too, but hold on, someone had a question over there.
I think really
Yep. Mm-hmm. That's only one Moore's law, right? 30% efficient versus 60, 70% efficient. You only need to double it once and you've caught up. Yep.
So with 50, you might get 25%.
Right.
So if we could get something like LTE from the media access perspective, as cheap as Wi-Fi, and without the large stations, it would be a really good step forward.
Sure.
It doesn't look like that we're getting new frequencies.
Yeah. Okay, so here's my claim, and I started off with a title page that said my alternative facts might not be true, so keep that in mind. But my claim is, as the capacity increases, and I have this slide here which you correctly predicted is the next thing I need to talk about. If we can pack more bits in and increase the throughput, the utilization of the available capacity will drop, because the demand is not rising as fast as the capacity. So at some point, the capacity will be so big that every increase in capacity will not increase bits transferred, it'll decrease utilization. If you decrease utilization, you decrease collisions. If you decrease collisions, you decrease jitter, and then all of a sudden things start working. And so my claim is we're going to actually cross over that point at some point in the next small number of years. And when that happens, all of a sudden you won't need to do all of this complicated stuff that LTE does. You can just do the dumb thing that Wi-Fi does, or the dumb distributed thing that Wi-Fi does, and you don't need this centralization anymore. The distributed system will actually be able to cover it. And again, this is my prediction. I can't prove that I'm right. So I do want to talk a little bit about what I call air space-time. People talk a lot about air time, and they want to reduce the amount of airtime used. And I think you've already sort of addressed quite a bit of it, but I want to focus specifically on MIMO, because I think, incidentally, this is a picture I found on the internet of a hypercube viewed through a hyper fisheye lens. So if this is I'm sort of talking about a 5-dimensional space of like what you're actually using, right? So one of the things, and Thomas is going to talk about this later this afternoon, I think, is if you can reduce transmit power by only sending the minimum transmit power you can get away with to talk to your client, you're reducing space usage, which overall frees up spectrum. And we have code that does this now. Thomas has done some pretty great work reducing transmit power per packet, so that if you have a nearby client and a faraway client, the nearby client you transmit to with less power, and that saves lots of space. Wider channels, if you use 80 megahertz instead of 40 megahertz, it reduces the time that you spend transmitting packets, but it increases the spectrum that you use, right? So air space-time, the total usage is the same if you use a wider channel or a narrower channel. Go ahead.
The problem is that the media access period is fixed in time, I think. It doesn't matter if you use 20 megahertz or 80 megahertz or 160, you need a certain amount of time to get the channel with the Wi-Fi protocol, and it's the same.
Right. Oh yeah. So right. So just to repeat for the microphone, the channel acquisition time does not increase. So if you're using less time per packet, it's actually wasting the channel acquisition time. That's technically true, but since 802.11n, we've had aggregation, and we just pack a whole bunch of packets instead of a single packet, and that amortizes the channel acquisition time over so many packets that it mostly doesn't matter anymore at modern usage patterns. That's my claim again. So anyway, it's interesting. So I went to a presentation by one of Apple's engineers, Stuart Cheshire. He's done a lot of really interesting stuff. But one of his quotes stuck with me, and I'm never going to forget it. He said, "Bandwidth is the ultimate perishable resource. You have to use it right now, or it's gone forever." And this is totally true with Wi-Fi spectrum. So if you are dragging something out in time just to save spectrum, what you're doing is increasing the probability that someone else will want to transmit at the same time as you. Right? It's a little complicated. If you squish it and use a wider channel, but send for less time, the probability of an overlap is less. So you have to kind of do a simulation to figure out why this is true. And I don't have time to do a simulation right now, but if you think about it enough, you can see that ignoring the problem of hidden nodes and stuff like that, which I don't have time to get into, but ignoring that problem, it's actually better to use a wider channel as much as you possibly can and stick everybody on all the spectrum. So right now we're dividing things up between a whole bunch of small channels. It would be better to have everybody using all the channels all the time and use less time per packet.
So as long as we use blocks and not slightly overlapping.
Right.
So it doesn't
Yeah, slightly overlapping is no good. Everyone has to be kind of on the same channel, so they're not partly overlapping destroys everything.
One question. So this is your claim, or this is something that you at Google Fiber test?
This is something that we have tested, and that, I mean, I don't have time to go in through all the stipulations, but in the big picture, that's what we want to aim for, everybody on the same channel. And so MIMO, my claim is that MIMO is magical and free. MIMO ties into Moore's Law, and when I started working on Wi-Fi, I thought MIMO was a bit of a gimmick, and I thought over long distances it wouldn't work, and I thought at low power it wouldn't work, and I thought through walls it wouldn't work, but all those things are false. If you use a really fancy chip and you orient your antennas the right way, it just magically carries more data through the same air. Yep.
So have you ever used a long range, let's say Wi-Fi link with more than 2x2 MIMO? Because typically MIMO for long range directional Wi-Fi links is done with polarization.
Right.
And you only have two polarizations which you really can use. 3x3 and 4x4 works in the house because of reflections in the house and difficult situations, but that doesn't work
Yeah.
for long range.
So it's true. For super long distances where you have point-to-point links, MIMO isn't absolutely the greatest for the polarization reasons you mentioned. For say 1,000 or 500 meters, it actually works okay. And I've tested that through walls and everything. And the more reflections there are, actually, the better MIMO works, which was apparently the engineers who came up with MIMO believed that it would only work if you go over long straight lines and had as little interference between the lines as possible. But they were surprised when they actually built the system that that doesn't work as well for the reasons you pointed out. But what works really well is when there's tons of reflections, because it turns out you have to invert a matrix related to the difference between distances that the lines have traveled, and if they've all traveled the same distance, it becomes harder and harder to invert the matrix without a lot of inaccuracy. If they're all doing completely different things, inverting the matrix is really easy, and so MIMO works better. So in a home, MIMO is great. If you're going over long distances, I would say we looked into a lot newer technologies like 30 gigahertz and 60 gigahertz. If you're doing point-to-point links, you can forget about MIMO and just use a super crazy wide channel that nobody is using way up there. You can use it for about 600 meters, and then 30 gigahertz, which is also. Yeah, 60 gigahertz. 60 gigahertz is a special frequency that is absorbed by oxygen, I believe. Yeah. So, but there are ways to do that. So I wouldn't necessarily recommend using MIMO for super long distance links, but if you're using undirected Wi-Fi nodes and you have a whole bunch of them, MIMO is really great. And I put a little star here because MIMO is free in that you can pack more into the same amount of space-time, and all it costs you is money. So it's free is a bit weird, but it's free in terms of space-time. Right. It does cost you size. So it's unlikely that you're going to end up with like million antenna phones until they all switch to 60 gigahertz or something. Yeah, I expect someone will invent a way to do 3 someday, probably. But what I would recommend is, this is why we have to talk about big meshes with lots and lots of really cheap access points, and those access points can have lots of antennas, and that's where that graph where if you put a 4x4 access point next to a 1x1 phone, you get pretty good speed. So the more access points you have with lots of antennas, the less you need your phone to have a lot of MIMO performance. And that's this is where Moore's Law pays off. Go ahead. Right. Yeah, 60 gigahertz doesn't go through walls, so that would be great as long as you've got. Yeah. You can have a lot of antennas with 60 gigahertz for sure, but it doesn't go through walls. So to do that, you have to have an access point in every room. There's another question there. Oh. Did I do what? Sorry? So yeah, beamforming is is really good actually on some chipsets right now, and I'll try not to mention specific vendors in this talk because I think it's being recorded, but some vendors are doing a really amazing job at beamforming with high degrees of MIMO. You can get 8x8 chipsets now for pretty reasonable price, and the distance boost that they get by beamforming is surprising. So yeah, it definitely works. A multi-user MIMO, I'm not as convinced about because of all that stuff I said earlier. Like if people don't all want to transmit at the same time because you've got such an abundance of capacity, there's nothing to multi-user MIMO about. But beamforming, I think, is a huge payoff. Okay, so I think I'm gone way over time now, but I only have, let's see, this one slide that I sort of want to quiz people. So back in the day when we were doing Wi-Fi meshes, it was all about the like multi-radio meshes. So you do the mesh on one radio and the access point on another one, or you do like, you bounce a signal on one radio and then you bounce it the next hop on another radio on a different channel. So you have these sort of expensive things. So I want to like pop quiz after all of this stuff. Is it better to have, given that the computation complexity is the same, to have two 2x2 radios or one 4x4 radio? Which one is more useful for building a mesh nowadays? Depends on your clients. That's true. If you don't have any, if your client is 2.4 gigahertz only, then you kind of have to have a 2.4 gig radio. But for just building the mesh backhaul, I mean. Number one? Right. So the answer was choose one because you can change the frequency and change channels so you have less overlap, right? So I would argue that number two is actually better. Based on all that stuff that I said, if you're using as much spectrum as you can, and the air space-time usage of two 2x2 radios is actually much larger, is twice as large as a single 4x4 radio. And it's kind of confusing, right? But when you add up the air space-time that is being used, 4x4 lets you pack twice as much into the same space as 2x2. So you have two 2x2 radios, you're doubling the space-time usage. If you double the number of antennas, you don't double the space-time usage. So in terms of taking the best advantage of your bandwidth, don't worry about using multiple channels. Put everything on one giant channel and use as much MIMO as you possibly can. What's that? Oh. So hidden stations can be a problem, but again, as the capacity increases and the utilization decreases, you should have a lot less trouble with hidden stations because you won't have as much overlap. Also, if you use Thomas's thing that reduces transmit power, and if you use beamforming, you'll have less trouble with hidden stations. So hidden stations are a little bit on their way out. I mean, it'll always exist, but it should cause progressively less and less impact on your network over time. So I think we have to sort of update our, like the worldview from 10 years ago is exactly correct. Hidden stations were a disaster. But the worldview today is that you need to sort of update your view on hidden stations. It's not necessarily as bad as it used to be. And that is the end. There were lots of questions during and I've gone over time, but if anybody wants to ask more things. Cool.